This is Errors and Uncertainties, Part 3, Propagating Uncertainties. What this means is calculating things from our measurements and then finding the uncertainty in our calculated quantity. Before we get into that, we need to make one little distinction. When we measured the length of the pencil in Part 1, we decided it was 5.4 plus or minus 0.1 centimeters. So this plus or minus 0.1, that was our uncertainty. Well, the full name for that is absolute uncertainty. So that's how much, at worst, we could be out by, or the range in which we're confident our measurement falls, actually as a value, usually with a unit, unless your quantity has no unit. So it's got a centimeters on the end here, because we could be out by up to 0.1 centimeters either side of this value that we've written down, 5.4. Okay, that's called absolute uncertainty. So this 0.1 is absolute uncertainty, and the absolute uncertainty in L we would call delta L. So we'd write like this. The absolute uncertainty in some other quantity, say V, would be delta V. We can also write down something called the fractional uncertainty. This is simply the absolute uncertainty divided by the quantity. So in this case, it's 0.1 centimeters divided by 5.4 centimeters. Whenever we find a fractional uncertainty, then the units cancel out. So the centimeters and centimeters cancel out here. Fractional uncertainties never have a unit. So they are simply the proportion of the quantity that we could be out by either side. So we could write that as a fraction. We could write it as a decimal. When we write as a decimal, we round it off to one significant figure unless the first digit is a 1. So here I've rounded it to two significant figures, 0.019. We could also write it as a percentage if we wanted as well. So we could just multiply that by 100 and get 1.9%. In your data booklet, you have got these rules for propagating uncertainties. We're going to look at these rules one at a time with an example of each. So starting with the first one. If we add or subtract things, then all we do is add the absolute uncertainties. So it's in your data booklet, you don't have to memorize it, you can see this. This is saying that if the thing you're calculating, y, is equal to two different values that you've measured, a and b, added together or subtracted, doesn't matter, then the uncertainty in y, delta y, is equal to delta A plus delta B. As an example, we might say we want to find the extension of a spring. So we measure the length of the spring when it hasn't got any mass hanging from it, and we get 3 centimeters, but of course that's always got an uncertainty. So 3 plus or minus 0.1. 0.1 centimeters is the absolute uncertainty. We then stretch the spring by hanging a mass from it, and we measure it and we find it's 4.8 centimeters plus or minus 0.1 centimeters. So finding the extension of the spring is easy. We just do 4.8 minus 3.0 to find out how much it's stretched. So that would be L2 minus L1. And the uncertainty in that L2 minus L1, that's easy. All we do is we add 0.1 centimeters from L1, 0.1 centimeters from L2. Even though we're subtracting the quantities, you add the uncertainties every time. Okay, a little bit more complicated, multiplying and dividing things. So let's look at the rule in the data booklet. If y is a, b over c, in other words, any quantities multiplied or divided. In this case, we've got a and b multiplied together, and then divided by c. Then what do? Well, we add uncertainties again, but this time we add the fractional uncertainties in the measurements to find the total fractional uncertainty in our calculated quantity. So delta y over y, that's the fractional uncertainty in our answer, is delta a over a, that's the fractional uncertainty in the first thing we measured, plus delta b over b, plus delta c over c. And it doesn't matter that c is on the bottom of the fraction, we deal with the uncertainties just the same, we add the fractional uncertainties. So, as an example, we've got a rectangle here. I want to find the area of the rectangle. So, to find the area of a rectangle, all I do is multiply the width by the height. So, A is W times H. W is width, H is height. So that's 3.5 times 1.7. That gives me 5.95 centimeters squared. But the question is, what's the uncertainty in that area? So to do this, I apply my rule. So I say delta A over A is delta W over W plus delta H over H. So now I just plug numbers in. So delta W is 0.1, W is 3.5. So delta W over W is 0.1 over 3.5, and so on. So that's what happens when I put my numbers in. And then when I stick that into a calculator, each of those fractions gives me these decimals, and that gives me a total of 0.08739. As always with uncertainties, if this was my final answer, I would round it off to one significant figure. So I would write that as delta A over A is 0.09, or I could write that if I wanted to as 9%. So what I'm saying from that is my value for the area could be up to 9% of the area either side of the value I've written down. Okay, but what is that in centimeters squared? Well, that's very easy. You just simply find 9% of the value that you found, 9% of 5.95 centimeters squared. So let's do that over here. So delta A over A times A just gives us our delta A, our absolute uncertainty. So we take our 0.08739 using my unrounded value, multiply it by 5.95 centimeters squared, and I get 0.52 centimeters squared. Again, as always, I'll round that off to one significant figure for my final answer. And then when I look at this, I say, okay, if I could be up to half a centimeter squared out, there's no point in writing down 5.95 for my area. That last decimal place doesn't really mean anything, so I'm going to round it to 6 centimeters squared. So my final answer is that my area is 6.0 plus or minus 0.5 centimeters squared. So using all my data, using not only the values of height and width, but also the uncertainty in height and width, I can find out not only a value for the area, but also an uncertainty for the area. So I know the range in which I'm sure my area lies. Okay, just one more quick example to highlight something. Let's say that instead of finding the area of a rectangle, I wanted to find the area of a triangle, which is obviously half of the base times the height. So half of W times H. So the area, well, that's going to have a different value to before because I've got this half in there. So it's half as big as it was before. But when I calculate my uncertainties, that half doesn't have any uncertainty at all, because that half is not a 0.5 something that I've measured. It is from maths. It is simply from that it's a mathematical fact that the triangle has half the area of the rectangle. So when we've got no uncertainty in that at all, so it doesn't change the uncertainty in the slightest. So everything we did with the uncertainty is exactly the same as before, and that means that the fractional uncertainty comes to the same number as before. We're still 9% out as a maximum, up to 9% out. So it does change one little thing about the uncertainty, which is, of course, the amount we could be out by is no longer 9% of the bigger area of the whole rectangle, it's 9% of that smaller area of the triangle. So the last step is a little bit different because it's 9% of 2.975 centimeters squared this time, which comes to that much, which of course we will round off to one significant figure. So our final answer is the area is 3.0 plus or minus 0.3 centimeters squared. Okay, and the last rule that's in your data booklet is what to do if you raise something to a power. So this means that you square something or cube something or whatever power it might be. So what do? Well, it tells you that if y, the value you're calculating, is equal to some measured value to some power n, then all you have to do is to find the fractional uncertainty in y, you multiply the fractional uncertainty in a times the power n. So my example is finding the volume of this sphere. And we happen to know that the sphere has a radius of 4.2 plus or minus 0.1 centimeters. Now, in reality, we'd be more likely to have measured the diameter, but I'm going to keep life simple for the video here and say we know this with this uncertainty. Okay, so the formula for volume of a sphere, 4/3 pi r cubed, so I just put my value for r into there, and I'll get my volume in centimeters cubed. So what about the uncertainty? Well, all I have to do is take the fractional uncertainty in r, so that's 0.1 divided by 4.2, but I need to multiply it by 3 because the r is cubed. So delta v over v is 3 times delta r over r. Where has this times 3 come from? It's come from the power here. Okay, notice we are multiplying the fractional uncertainty by 3. We are not cubing the fractional uncertainty. That is quite a common mistake that people make. We are multiplying by the power, not raising the fractional uncertainty to the power. Okay, when we do that, put the numbers in, round off to one significant figure, it comes out to 0.07, or we could call that 7% if we wanted. And then, as before, to find the absolute uncertainty, all we have to do is find 7% of our value, of our 310 centimeters cubed. So delta v is the fractional uncertainty, delta v over v, times v, which comes out to 20 centimeters cubed when we round off to one significant figure. That means the final answer that I would write down for the volume is 310 plus or minus 20 centimeters cubed. Okay, you've now seen one example of each of the rules in practice. I'm going to end the video there to keep it short. There are, of course, lots more examples, and some of those examples we might have to apply more than one of these rules together. So we might have to do things in more than one step. But this shows each of the rules. Another thing to point out on this is there was no uncertainty in the 4/3 pi, so that didn't come into our uncertainty calculation at all, because again, 4/3 pi isn't a measurement we've made. It comes into the formula, it comes from pure maths. That's what the volume of a sphere is. It's 4/3 pi times the radius cubed. It's only the radius which is a value we've actually measured, so has an uncertainty. Hope this was helpful. That'll do.